Right now, 23 billion kilometers away from Earth, a delicate assembly of metal and circuitry is coasting through the darkest stretch of interstellar space. Out here, the ambient temperature sits at a chilling -270 degrees Celsius, just one single degree above absolute zero. Yet, despite operating in this extreme environment, Voyager 1 remains operational. This is a probe built in the 1970s, packed with aging electronics, still communicating with Earth almost a half-century after its launch. To understand how that is physically possible, we have to look at the mechanics of temperature. When we step outside on a cold winter morning, the chill we feel is an active process called conduction. Billions of fast-moving air molecules crash against our skin, and with every collision, they carry away a tiny fraction of our body heat. In the cosmic void, this molecular theft is impossible. Interstellar space operates as a vast, near-perfect insulator. Heat is not aggressively stripped away by the environment, but must instead find its own way out. Because interstellar space is a vacuum, there is practically no matter to facilitate heat transfer. With barely a few atoms per cubic centimeter, there are no particles colliding with the spacecraft to steal its thermal energy through conduction. This comparison shows how heat behaves differently in the void. Conduction on the left requires a physical medium to move energy. On the right, in a vacuum, the only way heat can escape is through radiation. The spacecraft must slowly emit its internal warmth as infrared light, bleeding it outward into the darkness. Radiation is an incredibly inefficient way to lose heat. If you placed a hot cup of coffee in a perfect vacuum, it would stay warm for hours, slowly radiating its energy like a fading ember, rather than cooling instantly. This slow rate of cooling is the key to Voyager's survival. Because heat radiates away so gradually, the probe only requires a small, steady internal source of energy to maintain its operating temperature. That energy is supplied by 3 radioisotope thermoelectric generators, or RTGs, fueled by pellets of plutonium-238. Solar panels were never a viable option for this mission. By the time the spacecraft reached the distance of Jupiter, sunlight was already 25 times weaker than it is on Earth, leaving any solar-powered craft frozen and powerless in the outer solar system. Instead, the probe relies on the natural radioactive decay of its plutonium. This process releases a constant automatic supply of heat, which thermoelectric materials then convert into the electricity needed to power the spacecraft's instruments. This creates a self-sustaining thermal environment. Every calculation performed by the electronics and every active circuit produces residual warmth that circulates through the probe, keeping its internal systems within their operational temperature ranges. Generating warmth is only half the battle. The probe also needs a way to trap that energy using multi-layer insulation, or MLI. This insulation acts as a high-performance cosmic thermos. Wafer-thin sheets of mylar and kapton mirror the spacecraft's infrared heat back inward. Between these layers are microgaps of vacuum. With no air to bridge the space, conductive heat loss is blocked, trapping the warmth inside. This thermal management system allowed Voyager to withstand the relative heat of the inner solar system before successfully crossing the heliopause into the interstellar medium in 2012. Maintaining this thermal stability was a prerequisite for the mission's longevity, enabling Voyager to reach the furthest frontiers of our solar system, with its core electronics still functioning as designed. Physics has now dictated a countdown. Plutonium-238 has a half-life of roughly 88 years, which translates to a steady decline in power of about 4 watts every year, as the fuel slowly decays into lead. NASA manages this decline through a strict regime of power triage. Engineers have spent years systematically deactivating heaters and shutting down non-critical scientific instruments to preserve enough electricity for the core systems. This trajectory has a fixed endpoint. Sometime between 2025 and 2030, the energy levels will drop below the threshold required to run the transmitter. Once the core fails, the internal warmth will dissipate, and the probe will finally freeze. The end of the mission is a process of managed attrition. It is a slow, silent cooling, dictated by the predictable decay of its fuel and the unforgiving laws of entropy. When the final instrument powers down, the remaining internal heat will radiate into the void over several hours until the spacecraft falls completely silent. However, Voyager will not stop. In the vacuum of space, there is no friction to slow it down, meaning the probe will maintain its current velocity of 17 kilometers per second indefinitely. Roughly 40,000 years from now, this silent, frozen craft will make its closest approach to a distant star called Gliese 445, drifting through the darkness of a different solar system. It carries the golden record, a gold-plated copper disk containing the sounds and images of our world, a physical backup of Earth's existence designed to last for billions of years. As its power fails, Voyager transitions into its final role as an eternal cosmic fossil, a silent messenger drifting endlessly through the dark to prove that a curious species once reached for the stars.